All right, so for all of you who are learning at home this week, I'm trying to put together a video here which will help you with the molecular modeling mini lab. It's much easier to go through this stuff in person and kind of lay it out on the board. So I'm going to do the best I can here to give you the background that you need in terms of what makes water polar. You're going to look for similarities between this water molecule that you see here on the screen and the molecules that we're working with this week in class. So, before we figure out what makes water polar, it's very important to understand what a polar covalent bond is. Now, surely you've heard of ionic bonds where electrons are transferred from one atom to another. Sodium chloride salt is a great example of a compound that's formed by ionic bonds. Ionic bonds tend to be very strong, and ionic compounds actually dissolve in water very well because they have these charges and they form electrolytes, ionic compounds that conduct electricity when they're in solution. You also are probably familiar with covalent bonds. You would find these in a molecule of oxygen gas or hydrogen gas or many other examples. Carbon dioxide, carbon monoxide, all of those are examples of nonmetal compounds that form covalent bonds where the electrons are shared between atoms. Now, generally speaking, that sharing is fairly equal. Like the electrons will basically sort of go back and forth between the atoms, and they will be shared equally. They'll spend about the same amount of time around each of the atoms. But occasionally, if there's a sort of a moderate difference in electronegativity, and we'll come back to that in a moment, you will get unequal sharing of electrons. When the sharing is unequal, that basically means that the electrons are going to spend a little more time around one atom than they are another. Now, electronegativity basically is the ability of an atom to attract electrons in a chemical bond. The higher the electronegativity, the more that atom sort of wants electrons. So, in this particular example, the oxygen atom has a higher electronegativity than hydrogen, so it will attract electrons more strongly to it in a chemical bond. But the difference in electronegativity between the two atoms is not enough to pull that electron all the way away from hydrogen, like you would see in an ionic bond. So we're left with what we call a polar covalent bond. So the particular polar covalent bond that we're looking at here is this bond here between hydrogen and oxygen. And what happens is that the electrons, because they spend a bit more time around the oxygen, they'll sort of hover in orbit nearest to the oxygen atom and away from the hydrogen atom. That gives the oxygen atom a partial negative charge. You see this symbol here, which is the Greek letter delta, which denotes a positive charge, a partial negative charge, rather. And over here, we have these two partial positive charges on the hydrogen atom. And what this essentially does is it creates two different sides, and I'm going to change my color here, two different sides of the water molecule. So over here, you've got a negative side, and where you see the hydrogen, you've got a positive side. Now, these positive and negative charges are not full positive and negative charges, so they don't behave exactly like an ionic compound, like salt would, but they do attract those opposite charges, and that is a lot of what gives water its unique properties. Its ability to form hydrogen bonds, its higher than expected melting and boiling points, a lot of the properties that water has, including the ability of ice to float on water, are due to this particular structure. So, the things that make water polar are as follows. First, the bent shape. And that's actually the name that scientists give to this shape for a molecule. You can see here that it's bent. I believe the angles between the oxygen and hydrogen are about 109.5 degrees, but the angles don't matter so much as the fact that this molecule, rather than being straight, is bent. And so that allows the hydrogen to sort of occupy its own side of the molecule. And the second thing that makes water polar is the polar covalent bonds. And in those polar covalent bonds, the electrons are pulled toward oxygen. Now, there are some molecules that have polar covalent bonds. Methane is a great example that comes to mind. That's what you have if you work with natural gas in your house. And all of the polar covalent bonds cancel out. Basically, they just all meet in the middle, and there's no sort of charge in one direction. Here we have a distribution of charge and a distribution of shape. So we're actually able to create positive and negative sides of this molecule. So the take-home message here in terms of what makes water polar is that this bond here between the hydrogen and the oxygen, which we call a hydroxyl group, is what makes water polar. So as a rule of thumb, and this is a bit of an oversimplification, but as a rule of thumb, we are going to look for as many of those groups as possible to find a polar molecule. I'm going to spoil this for you a little bit. Glucose, the first example in this week's activity, is actually a polar molecule because it has a lot of these hydroxyl groups. You'll also notice that polar molecules tend to dissolve in other polar molecules. So glucose and other sugars dissolve really well in water because while they're not ionic compounds, while they're not going to separate when they dissolve, they are polar molecules. And we have the very simple rule that I'm going to put down here, and we'll do this in blue. Like dissolves like. That is, if you have a polar substance, it will dissolve in water because water is a polar solvent. Something like oil that is not polar will not dissolve in water because they are chemically too different. So, I hope this was a good summary of polarity and specifically what makes water and other molecules polar. And if you have any questions, you know where to find me. So hopefully this helps, and have a great week.